I, which is equal to I wrote the I value 145.98, and 2 because of what? Box B. Okay, so this will be equal to 5,000 multiply 19.027 divided by 145.98 divided by 2. So it's equal to 325.849. And this is pound per inch. Okay, so point A is straightforward. Okay, point A is straightforward, right? Okay, now we are going to look at point B. Okay, you're going to look at point B. So at point B, which terminal do we actually use? Do we use terminal 4 or do we use terminal 2? Okay, knowing at point B, right, if you were to look at the arrows, right, the arrows are running in the what? Horizontal manner, right? Okay. If you look at the arrow that's running in a horizontal manner, then T2 is the terminal we should use. If you look at a proximity, which is the closeness, then you should use T4. You see what I mean now? You can, which one should it be? Is it T2 or is it T4? So where does it origin? Okay, so that's where I draw this diagram. Okay, it is not just dependent on the proximity of the terminal, but more important is the what? Is the shear flow. So if you look at point B, right? If you look at point B, the shear flow are running horizontally. If that's the case, we have to use what? T2, and we don't use T4 because T4, the shear flow is running what? Vertically. Can you all see that? Okay, so this is decision making now. Formula is easy. Shear flow VQ over I. V is constant, I is constant. The first moment of area is critical. Okay, so that's where we have analysis. Are we clear? So if that's the case, then by looking at the diagram or by looking at the design of your shear flow, you know that you have to use what? T2. Okay, so for point B, okay, T2 is the terminal because of the orientation of the shear flow. Okay, because of the orientation of the shear flow. Okay, so now we want to find point B. Okay, so to find point B, we are going to focus on this area over here, right? I'm coloring in red now. Okay. Are we clear? It's not just the closeness, yeah. More important is the direction of the what? Of the shear flow. Okay. So now at point B now, we want to find the QZ of point B. Okay. So we have our width. So now our width is 5 and 5 is 10. Our depth is equal to 0.5. Now, Y bar is where we have to be careful. So we know that there's a certain distance from hold on, let me change color. We know that from a certain distance, from here to here, this is equal to 3.70946. 3.70946. right? And then if that's the case, right, the distance from here to here would be 8 plus by 0.5 minus by 3.70946. Okay, so this will be 8 plus by 0.5 minus 3.70946, which is equal to 4.79054. Let me do it again. 8 plus 5.5 minus 3.70946. 4.79054. Okay. So we know the distance from here to here is 2.5. Okay, because not 2.5. It's equal to 2.25. Right? Because of half of 0.5. Right? So 0.5 divided by 2 plus by 2 is 2.25. So the y bar is equal to 4.79054 minus by 2.25. So this will be equal to 4.79054 minus by 2.25 times by 0.5 times by 10, which is equal to 12.7027. Now you can see over here, it is very easy to make mistake. The most important thing that I learned while doing so many examples is you have to get your data organized. Once your data is organized, things are really easy. Okay. So I forgot to write earlier. So we know that point B is box beam, right? Because we have two arrows coming to terminal, so you have two, okay? So we know that we are going to have 2Q, right? So when that's the case, small q at point B, again, straightforward, V divided by I, which is 145.98, multiply by 12.7027, and then divide by 2, because the 2 over here, because we declare that it is box B. So this will be equal to 5,000 times by 12.7027 divided by 145.98 divided by 2 is equal to 217.542 pounds per inch. Okay, so that is for point B. Then the next part of the question state that determine the maximum shear flow in the cross section. Okay, so by looking at observation, right, the thickness of the beam is constant. Everyone is 0.5, right? Everyone is 0.5. Okay, everyone is at every section, right? The thickness is 0.5. So for this case, where maximum first moment, maximum shearing stress will occur is definitely at the centroid, because at the centroid, the first moment of area is the biggest, is the largest. Okay, so coming from here now, okay, so I'm going to take the whole figure again, right? So what we know is the centroid, the geometric centroid, right? And we are aware is 3.70946. Okay, so I'm going to show you two ways of looking at it. We can do it either from the top section or the bottom section. The answer will be the same. And we know that this is at the centroid, right? It is at the centroid. Right? It is a what? Box beam analysis. Okay. Now, if we look at the top part, okay, so if we look at the top, it's very straightforward, right? So, for example, I'm just going to sketch our geometric centroid, right? So you have Q at one end and Q at the other end, right? So this is our top. If we focus on the bottom section, right, you also have Q on one side and Q on the other side, and is known as the box beam. The only thing you have to do is you have to consider the entire first moment of area at the bottom section. Very clear? Okay, you have to combine all the terminals over here. Okay, so you have to consider the entire first moment of area. Okay, so let's calculate the first moment of area from using the top. Okay, so Q about the z-axis. So the width is 11. The depth is 0.5. And then we have 3 point bracket 3.70946 minus by 0.5 divided by 2 plus. So now is the vertical web 2. Okay, so the width, that's the easy part. Now the depth is 3.70946 minus by 0.5, right? And then again, we have to do 3.70946 minus by 0.5, and then the whole thing divided by 2, right? So the standard form of the formula is QZ is equal to width that y bar. So to write down here, this is our width, is our depth, is our y bar. This is our width, this is our depth, this is y bar. The 2 over here is for the left and right. Okay, so this will be equal to 3.70946 minus, turn on my calculator. 3.70946 minus 0.5 divided by 2. 10.5 times 11 is equal to 19.027 plus by 3.70946 minus 0.5. Left and right equation are the same. Squared divided by 2 times by 0.5 times by 2 is equal to 5.15. 5.1503. Let me do it again. 2 minus 3.70946 minus 0.5 squared divided by 2 times 2 times 0.5, 5.0. Yep. So this will be equal to 19.027 plus 5.1503. It's got 24.1773 inches cubed. Okay. Now, if we were to consider the bottom, okay, so now I'm going to do the bottom. The answer has to be the same. Okay, so now if we were to consider the bottom, so we know that the distance from here to here is equal to 8 plus 5.5 minus by 3.70946, right? So 8 plus 5.5 minus by 3.70946. You have 4.79054. Let me do it again. Okay, so it's 8 plus 0.5 minus 3.70946, 4.79054. Okay. So at the bottom, so QZ, so I'm going to take the major wet first, 2, with his 0.5, depth is 4.79054, right? And then